Well, good morning, everyone. Today, we're going to start looking at the full convergence test for a power series. Now, up till now, we've just been looking at little pieces of it and looking at all the different skills that you're going to need to make the whole thing go together. But this is the first time where we're actually going to take a look at the convergence for a power series. It can be a little bit of a lengthy process. So when you see this on the AP test, it's probably going to be the only question, or should you have a full convergence test, it's probably going to be the only question on, that part. It's not a multi-part question. In any case, let's go ahead and take a look at what we have. So for atmospheric reentry, John Glenn's Friendship 7 needs to rotate to a specific angle to ensure that the heat shield captures the maximum amount of heat. Otherwise, well, it's goodbye Friendship 7. So suppose the angle of reentry can be computed by this series A equals the sum of x minus 1 to the n over n plus 1 multiplied by 3 to the n, where A is the angle produced by 4x amount of thrust. The question here is what values of x, what amounts of thrust really, does the series provide reliable angles? Okay, well, here is a review of the ratio test, I think for a third time. All you need to do is find the limit of an plus 1 over an. If that limit is less than 1, the series converges. If the limit is greater than 1, the series diverges. If the limit is equal to 1, then the ratio test is inconclusive. For our purposes, we're going to find the absolute value of the general terms to create our interval of absolute convergence. In fact, let's just do it. Find the interval of absolute convergence for this series, x minus 1 to the n over n plus 1, 3 to the n. First thing we do is start off with the ratio from the ratio test, and don't forget we're doing absolute values for absolute convergence. To make things a little bit more compact, we're going to multiply by the reciprocal of the general term an. So it's a of an plus 1 multiplied by the reciprocal of an. And we want to force that to be less than 1. Okay, so let's try to simplify each piece separately. And that first piece is the x minus 1 to the n plus 1 over x minus 1 to the n. You'll remember that the x minus 1 to the nth power is going to cancel out, leaving us with an extra power on the numerator. So I can simplify that to just the absolute value of x minus 1. Since there's no n involved with the absolute value of x minus 1, we can put that on the outside of our limit. The next piece here is the n plus 1 plus 1, and that's going to be under n plus 1. Now there's no way to actually simplify that, and both expressions have an n, so we've got to keep that inside the absolute value and inside the limit. And the very last piece here is 3 to the n over 3 to the n minus 1. Remember that this simplifies very similar to the way that we did x minus 1 to the n plus 1, only this time we have an extra 3 on the denominator. So since the 3 is on the denominator, that's a 1/3. And since 1/3 doesn't have any n's, we can just put that on the outside of the limit as well. That gives us the absolute value of x minus 1 over 3 multiplied by the limit of n plus 1 over n plus 2. Now inside the limit, we're going to divide each piece by n, so the resulting limit is 1 plus 1 over n over 1 plus 2 over n. Both of those limits are 0. 2 over n goes to 0. 1 over n goes to 0. So the limit is the limit of 1 over 1, which is just 1, leaving us with the absolute value of x minus 1 over 3 is less than 1, which simplifies to the absolute value of x minus 1 is less than 3. We compare that to x minus center is less than the radius, and it doesn't seem like we need to do any more algebra to make those two inequalities fit with each other. So the center is 1 and the radius of convergence is 3. The interval for any power series is x element of center minus radius to center plus radius. So we've got, where we get the interval of absolute convergence is x between -2 and 4. Scrolling down, we are testing endpoint convergence because the ratio test was inconclusive at those endpoints. Okay, if you were to substitute -2 into series, the ratio test would give you 1, and if you were to substitute 4 into the series, the ratio test would also give you 1. So if the interval of convergence of absolute convergence is -2 to 4, then at x equals -2 and x equals 4, the ratio test is inconclusive. So remember that, the ratio test is inconclusive. So what we're going to do to start to complete the process of finding the interval of convergence is we're going to substitute -2 into the general term to create the series that results when x equals -2. So here's the series that we started off with. We're going to substitute -2 for x, which means that the series is going to be -3 to the n on top of n plus 1, 3 to the n. Now, that -3 to the n, we've talked about simplifying that before. We can use properties of algebra to separate the -1 from the 3 to the n. So that's the same thing as -1 to the n, 3 to the n. And so very neatly, when we cancel out those 3 to the n's, we just get the series of -1 to the n over n plus 1. Okay, so this is what we do at the endpoints. We substitute the endpoints, we simplify the series, and we get a series that doesn't have an x anymore. It's no longer a power series. So the resulting series should look like -1 to the n over n plus 1, check. The first thing that I would say is to make sure that the general term goes to 0, and it does, 1 over n plus 1. As n gets bigger, the denominator gets bigger. So since the denominator gets bigger, but the numerator doesn't get bigger, the general term is going to go to 0. The general term is going to go to 0, which means that we're failing the nth term for divergence. I always try to make a quick check of the nth term test for divergence, because if it fails that, then I don't have to do a whole lot of work to show that this converges. Okay, so does a series converge or does it diverge? And let's perform the necessary test to check. So this series, -1 to the n over n plus 1, is an alternating series. And you can tell because you have -1 to the n, and n will go to both positive and negative numbers. The exponent is both positive and negative, depending on the value of n. So the series alternates. And for an alternating series, we use the Leibniz test to show convergence or divergence. Remember, the Leibniz test is conclusive, so it'll show for sure whether or not an alternating series converges or diverges. Don't forget to write the name. The limit of the absolute value of the general term is just a limit of 1 over n plus 1. Remember, to make an alternating term not alternating, all you got to do is replace the -1 to the n power with a 1, or just to leave it off completely. This limit, 1 over n plus 1, that's equal to 0. And if I get a 0 in the Leibniz test, the conclusion is that the series is going to converge. So we've done the test for the first endpoint. So the series -1 to the n over n plus 1, that's going to converge by the Leibniz test. Not bad. Okay, notice how this is a combination, or this is exactly what we were looking at in the previous days and all those previous limit lessons where we were looking at non-power series. This is why we do them. It's because when we substitute x, we get something that is not a power series. Okay, move on. Substitute x equals 4 into the general term to create the series that results when x equals 4. You'll remember that 4 was the right endpoint of our series. So let's substitute 4. Start with the series from the beginning of the problem. Substitute 4. Simplify. Notice that we can cancel out to 3 to the n. And that gives us the resulting series, the sum of 1 over n plus 1. Now, does this series converge or diverge? Looking at this series, I only have a polynomial on the denominator, and there's nothing else involved. No exponential, no factorial, no square roots, nothing funky. Just a polynomial in the denominator. Maybe the first thing I should have said, was the general term 1 over n plus 1 trends towards 0. The limit is 0. So the series fails the nth term test, which just means that it doesn't outright diverge. We can't just stop with the nth term test. So we've got to keep testing. Okay, back to the series. 1 over n plus 1, only polynomial pieces to it, so we're going to look for the closest p-series to it and use the LCT test. To find our comparative p-series, we're going to start with our a, which is the general term in the series, and then we're going to take everything away except for the lead term. At this point, if there were any constants left over, we would have stripped those away as well. If there was a n in the numerator and the denominator, we would have gone ahead and simplified that as well. But as it is, we just have 1 over n, which we're going to call b. Now, 1 over n is a p-series, and the p is equal to 1. So this is a diverging p-series. B is the diverging p-series since p equals 1. Since p is equal to 1, this particular series has a name, and it is called the Harmonic Series. If you want to impress your calculus teacher, you can call it the Harmonic Series. That only applies to 1 over n. So to start the limit comparison test, we're going to find the limit for a over b. If you want to treat this like the ratio test and just multiply by the reciprocal of b, that you're perfectly within your right to do that, because it will simplify a little bit easier. Okay, simplifies to n over n plus 1. Then we're going to divide everything by the highest power, which is n to the first power. Okay, after we've divided everything by n, we notice that the only place we have an n now is 1 over n. And the limit for 1 over n is 0. So what we're left with is 1 over 1, and that limit is just 1. Conclusion-wise, since the limit 1 is between 1 and infinity, and since b diverged, that means that the series for a diverges. So down over here, the series 1 over n plus 1 diverges by the limit comparison test. So in summary, we've got this series is going to converge absolutely for -2 to 4. It's going to converge at x equals -2, and it's going to diverge at x equals 4. Therefore, the interval of convergence is a bracket at -2 for the convergence and a parenthesis around -4 to show divergence. That is the full interval of convergence. And think about this. We did all of that work for, it looks like 8 symbols here. 8 things that you're going to write for your final answer. All of that work. So that takes us through the entire how to find an interval of convergence. So we are ready for some important ideas. When you're trying to find an interval of convergence, the first thing you need to do is to make sure that you are or you're not looking at a geometric series. And the reasoning is because when you analyze a geometric series, there's a lot less work for you to do. You don't need to check the endpoints. All you need to do is find the ratio and solve the ratio is less than 1. If you use a ratio test on a geometric series, then you need to do everything involved with the ratio test, which is a much longer process, and you're wasting your time on your AP test. So don't use a ratio test for a geometric series. Use a geometric series test for a geometric series. If you find yourself looking at a series that's not a geometric series, then you need to redo the ratio test. So the first thing is to use a ratio test on the absolute value of the series to find the interval of absolute convergence. Substitute the left endpoint to check the left endpoint for convergence. When you do that, you have to use the nth term test, the Leibniz test, the p-series, the limit comparison test. You might want to use the integral test or even the root test, which we don't even discuss here in this series. Maybe in the future we'll have a supplemental video of the root test and I'll put it over here, but who knows. You're going to repeat the process for center plus radius to check the right endpoint. And then you're going to combine parts A, B, and C to form the interval of convergence. So let's check our understanding with a couple of thoughtful problems here. And the first one is to find the interval of convergence for 2x minus 1 to the n over 2 to the n. Now I look at that general term and I say to myself, well, first I say, hey, is that a power series? And yes, it's a power series because the general term has an x. Now the other thing I say is, where do I see an n? And I see only an n as an exponent. So that cues my brain to tell me that I'm looking at actually a geometric series. Now that I know that it's a geometric power series, well, actually, let's pretend that you didn't know that it was a geometric series based on analysis of the general term. If you don't recognize it, you're kind of doomed to write out the first 4 terms of the series. Now you're not, it's not a doom thing, really. I said doom, but really it's just going to cost you a few moments to write out the first 4 terms. So here's our first 4 terms, and I notice that to get from one term to the next, the consistent thing that happens, the only thing that happens, is I multiply by 2x minus 1 over 2. That's a geometric series. Now that I know it's a geometric series, I can use the geometric series routine. And that just involves solving the ratio less than 1. The ratio was 2x minus 1 over 2. So I just need to solve the absolute value of 2x minus 1 over 2 is less than 1. Remember, we're looking for a statement that says the absolute value of x minus a center is less than the radius. And that's not what we have here yet. We have 2 times x, the whole thing divided by 2. This is not the same form, so we're going to use some algebra to simplify. The first thing you're going to do is multiply by 2. If you think back to your algebra days, maybe 3 years ago, if you have an inequality, you can multiply both sides by the same number. If the number happened to be negative, then you need to switch the inequality to the other side, but that's not going to happen here because we have absolute values. So let's multiply both sides by 2. And that gets us the absolute value of 2x minus 1 is less than 2. Now that's not quite there yet too, because we have 2 times x and not just x. So in order to simplify that, we're going to divide by 2. My gosh, why didn't I just divide by 2 right inside the absolute value? Yeah, that would have made things a little bit easier, wouldn't it? Okay, so let's go ahead and simplify that. Turns out I kind of went the long way around here. You could have simplified this a lot faster, but whatever. Absolute value of x minus 1/2 is less than 1. That does look like x minus a center is less than a radius. Now that we know my center is 1/2 and my radius is 1, we know that we're looking for x between center minus radius and center plus radius. 1/2 minus 1, that's negative 1/2, and then 1/2 plus 1, well, that's just 3/2. So we're done here. This is our interval of convergence. Because this was a geometric series, there was no need for us to check negative 1/2 and 3/2. We already know that it's going to diverge there. Okay, let's move to the second one here, which I have a feeling is going to be a little bit longer. We've got find the interval of convergence for root n plus 1, x minus 1 to the n, 5 to the n. And we'll do the exact same thing. First thought here is, do we have a power series? And I definitely see an x, so this is a power series. Is this a geometric series? Well, if you take a look, we have root n plus 1. And if we have an n any place other than an exponent, it's not going to be a geometric series. Now that we know we have a power series that's not geometric, we are going to use the ratio test to find the interval of absolute convergence. We're going to set up with the ratio that we need to solve. Okay, an plus 1 over an, and just like before, or with the last time we did this ratio test, I think we did this for the LCT test too, we're just going to multiply by the reciprocal of the general term. And then we want to force this to be less than 1. Now we're going to take piece by piece and we're going to see what we can do here. And the first piece I see are these square roots. And these square roots really, well, we can't do anything with them. They have an n, so I'm going to put them inside the square root, or inside the absolute value for the next step. What I will do is make sure that I have one square root, so n square root of n plus 1 up n plus 2 over n plus 1. The next part here is the x minus 1 to the n plus 1 power. We know how that's going to simplify. The n powers are going to cancel out, and that's going to leave me with an x minus 1. No n's involved, so I'm going to put it outside the limit in absolute values. And then the last piece we have here is 5 to the n over 5 to the n plus 1. We know how that's going to work. The 5 to the n powers are going to cancel out, leaving me with 1/5, which no longer needs to be part of the limit. Okay, we have simplified this, and the only thing we need to do is take the limit of the square root of n plus 2 over n plus 1. You know what I'm going to do here? I'm going to divide everything inside that square root by the highest power of n, which is just n. That gives me the pieces 2 over n and 1 over n. Both of those are going to go to 0. And we get left with the absolute value of x minus 1 multiplied by 1/5 multiplied by 1 is less than 1. I'm looking for x minus center is less than the radius, so I'm going to multiply both sides by 5. Now that this looks like x Now this looks like x minus the center is less than the radius. The center is 1, and the radius is 5. Now any interval of convergence is going to be center minus radius and center plus radius. Center minus radius is -4, and center plus radius is 6. So this is my interval of absolute convergence. And wow, we've spent some time on this one already. Don't you wish this was a geometric series? Well, we're not done yet. We need to check our endpoints. So our first endpoint is x equals -4. Here's our power series that we started off with. We're going to substitute -4. We're going to simplify -5 to the n power. And then we're going to cancel out the 5 to the n powers. And here's our resulting series. The series, the sum of -1 to the n plus 1. Now I know you're looking at that -1 and saying this is a alternating series. You're correct. This is an alternating series. So if you wanted to use the Leibniz test, go ahead. I'm looking at this a little differently, and I'm saying, hey, square root of n plus 1 doesn't go to 0. So whether or not it is a alternating series doesn't even matter, because the general term does not go to 0. So I'm going to use the nth term test. So the limit as n approaches infinity of the general term -1 to the n power root n plus 1, that's just going to get bigger and bigger, and it's going to get bigger in the positive direction and bigger in the negative direction. So the limit doesn't exist, which is not the same thing as 0. Therefore, the series is going to diverge at x equals -4. Now it's time to check the right endpoint, x equals 6, and this is going to go along exactly the way we did the left endpoint. Start with the series that we started off with. Substitute the endpoint, x equals 6. Keep on simplifying, and now we can analyze. We've got the sum of square root n plus 1. Now I know that that limit is not equal to 0, because as n gets bigger, the square root of n plus 1 just gets bigger also. So we're going to use the nth term test yet again. Find the limit of the general term. These terms go to infinity for sure, and infinity is not equal to 0. So just like at x equals -4, the series is going to diverge at x equals -6. And when we put it all together, we get the interval of convergence. The interval of convergence here is x between -4 and 6, not including 4, -4, not including 6. And that is where it is. Now you'll notice, important, you'll notice how much work we needed to do here when we had a power series that was not geometric. And then you compare that with how much work we had to do for a power series that was geometric. And if you take a look at those two workflows, I think you can see why you don't want to use a ratio test for a series that is not geometric. Or you don't want to use a ratio test for a series that is geometric. So that's our look at it today. You're definitely going to need more practice doing this. But if I'm honest with you, I think the steps that you need to do here are pretty well defined. There is a process here. The process is, really only 4 or 5 steps. True, you could get bogged down in a lot of algebra. So this is one of those places in calculus where your algebra skills are really going to determine your success in the class. But, that's pretty much all of calculus anyways. So that said, good luck to you, and we'll see you next time.